I'm Robin Johan. I am the head of engineering at a VC focused on agri-food tech. And I am working on a reinforcement learning project with a digital health company. And I'm currently at ICLR. And I'm glad to be here. Thanks so much for having me.
Okay, my name is Alexis Krop. First question, can you see my screen? Yeah, because I'm losing.
Yes.
I have, yeah, I already complained that I have 3. You cannot hear me?
No, we can. It's good.
Okay.
It's all good.
Yeah, so I have 3 screens here, so I can trying to coordinate between those. My name is Alexi, and I am CTO at the local startup called Dispersed Traffic, and we are helping cities to reduce CO2 emissions by optimizing traffic flow at the intersections. We are using computer vision and reinforcement learning. So if you're interested in the problem we are working on or technologies we are using, please contact me. We are open for all kinds of collaborations, and you can contact me on a Slack channel. I guess everybody is on a Slack channel for this meetup. And also you can contact me on LinkedIn, Twitter, like any other social network. I'm pretty public, like I'm open. And also we have a contact information for both Robin and myself at the last slide. And I guess I will start here with like a competition description, but also why I was interested in that. So as I said, we are using reinforcement learning in our company, and I was very excited to see that Kaggle had these new types of competition available, and that's why I reached out to Robin, who's pretty famous in our local community as somebody who's super interested in reinforcement learning. And he also has his own podcast. He hasn't said that about himself, so I have to. I listen to every episode, and I encourage you to do so. It's very interesting stuff. And so it's all about reinforcement learning. And Robin will talk about that part in details, but we will see that it's actually not a winning solution, unfortunately, in this specific case. And we'll see what works and what's not. And I'll start with a competition description. So first, here is a disclaimer. Like I got pictures, code, and most of the information in this presentation from all different sources, from public notebooks, websites, forums, and I tried to put all the links on the slide, so you can basically find the source of this information. But if I missed anything, I'm really sorry. I don't claim any rights for any information presented here today. But this specific screenshot that you can see here is taken from my page on Kaggle, and as you can see, there are not too many teams in this competition. As of yesterday, it was 357. And the reason for that probably is that, first of all, this is a knowledge competition. Also, it means that there are no money prize available and no deadline. And that's why probably there are not too many people competing in that. There is also maybe some people are afraid of joining that competition because it's a new type of competition called simulations. And how is it different from all other competitions that we discuss on this meetup? Basically, as you probably know, since Kaggle launched exactly 10 years ago in April 2010, most of the competitions were in supervised learning. And it means that you have to submit some kind of like a classification or like an answer-vertical classification problem or model. So you have to submit a CSV file or pre-trained model. In this case, you need to submit a file, just one Python file, and it's supposed to be just one file with one function, and we will discuss what it should look like, what the input and output parameters. What else is interesting about this competition, that the evaluation metric here is not some kind of loss function. It's actually a score that is calculated based on how good the agent that you build play against other agents built by your competitors, which is very unusual. And also another reason why many teams probably already dropped it from this competition is because it's on rolling window, meaning that if you submit your solution today, it will expire in 2 months. And there is probably good reason for that, because as you can imagine, if you have like 1,000 teams competing, what Kaggle does, you have one submission per day, a limit of one submission per day, and overnight Kaggle runs all agents against each other, or probably like all the time. And if you have 1,000 teams and 1,000 agents running against each other, that's a lot of computing resources. And that's maybe another reason why there are not too many teams here. And as you can see, our last submission was a few days ago, and it has a public score of 153, and it puts us somewhere in the middle. And we will discuss why is that and what solution did we use. Actually, there's a hint right there. It says MiniMax agent. So let's talk about the game itself. So what we are trying to do here is to play Connect4, and probably like almost everybody knows the rules, but because I was one of the people who probably like very rare occasion where I didn't know the rules, so I will go over that really quickly. So the rules are extremely simple. It's a 2-player connection board game with perfect information for both sides. And we have a grid with the 7-column and 6-row where players can drop their pieces from the top. So we have 2 players and 2 colored types of coins or checkers. I will be using all of these terms interchangeably here, so we can call them checkers, discs, coins, pieces, whatever. And pieces, they fall straight down to the lowest available space in that column. And goal of the game is to be the first to form a line of 4 pieces with 1 color. And the winning lines can be horizontal, vertical, or diagonal. And then, like, this is a case where one picture worth thousands of words. As you can see, the red player wins here with the diagonal line. So when we play this game, there are different ways of approaching that problem and trying to win the game. And the first is like very simple agent that you can run. It's just basically a random agent that drop pieces randomly. And funny enough, it actually can win sometimes. And it actually can win sometimes like a decent agent, not a strong agent, obviously. But to build a strong agent, you need to put some kind of logic into that. And we will go over some of the rule-based. I will go over some of the rule-based solutions, which is one step ahead, MiniMax, open book, and perfect game. And Robin will go over reinforcement learning piece. So just a quick overview. One step Lookahead is something similar to what toddlers do. At least that's what I think, based on how my 4-year-old son played this game. So what they do, they take a win if it's presented, like if they can see obviously that there are three pieces in a row, and then they can just add one more piece there and win, and they block the obvious loss. Like if they can see that now they will be losing in the next step, they basically block it if they can. And otherwise, they just randomly drop like a coin in different places. So MiniMax is something that most people do, and probably that's something that we can understand pretty easy. We use the same technique when we play any game, chess, checkers, so any other adversarial game. Basically, what we are trying to do here is we are looking at all the options we currently have, what moves we can make, and we predict what opponent will do if we choose a specific option. Obviously, good players, they look many steps ahead, and that's why it's also called end-step look ahead. And we will talk about that, and we will see why it's such a strong solution for this specific competition. MiniMax is just like a variation of MiniMax, and we'll talk about that as well. And reinforcement learning is basically the type of agent where it can play against itself, and in this way it's self-learning, and if it plays thousands, maybe millions of games against each other, it becomes better and better. So you always pick the best winning agent and play it against itself once again and once again. But I guess most of you already know that. And that, for this specific game, we also have an open book solution. It means that we can evaluate every single state and know how to move in every single state of the board. Although we do have 4 trillion different combinations, it's still possible. And the only thing that this solution cannot be used here, just because of the limit on resources that we have, and we will discuss that. But this is basically almost a perfect game. The perfect game is open book with the first mover advantage. The thing is that Connect4 is solved game, meaning that you can always win if you have if you're player number one. Yeah, well, as I said, we will go over all of these solutions. I have one slide on reinforcement learning. I'm sorry, if anybody has any questions, I think that Alexei didn't say that you can interrupt at any point, especially. And can I ask you, Robin, maybe, or somebody else to watch the chat if there are any questions to read? No questions? Okay, yeah, well, it's straightforward. Yeah, it's straightforward, I guess. So,
sorry, can I ask a question?
Yeah.
So you said Connect4 is a solved game, and white wins, basically. Player one wins. So in this competition, I guess the main idea is that you can't use these open book solutions, and therefore it becomes interesting again. Is that right?
Yeah, that's exactly right. We do have 2 limits. We have a limit on amount of memory that we can use and on time. So that's why it becomes interesting. Otherwise, like, there is no point of playing. Actually, like, spoiler alert, actually people were able to use both of these techniques, open book and MiniMax, to make it perfect. So there is a perfect player, even with all of these limitations that Kaggle did. But just because you asked, like, that's something that people use. And,
I naively assumed that Connectx X is not equal to 4, and that would make the game more interesting. Is that not the case?
It is the case. The only problem is that, as we will see on the next slide, or maybe 2 slides from now, the default parameter, so like the agent plays Connect4 just because that's what everybody else plays. So, Okay, I will talk about that later. So yes, you are right. It can be anything, but for this specific competition, right now it's Connect4.
I understand.
Yeah. Okay, so as I said, I have one slide on reinforcement learning, although Robin will go over that in more details. But I need to introduce some vocabulary just because all agents in this competition, even if they are rule-based, they are using the same vocabulary. So when we are talking about reinforcement learning, in a typical scenario, we have an agent and environment. And the agent can get a sense of what is happening in the environment by using state information. What exactly we get as an input state depends on the environment. So in our case, it's just the state of the board, meaning that and as we said, this is a perfect information game, meaning that everybody can see the full board and everybody has all the information about the environment. But let's say if you're talking about like more general example, let's say autonomous vehicles, the information about the state would be data from cameras, data from LiDAR. Based on that information, agent can take an action. And in our case, the only action that we can do is just drop a coin in a specific column. Like we can choose one of the columns and just give a number. But for autonomous vehicle, it could be like several different actions. Let's say it can change the speed, or it can steer a wheel left, right. So there are different options for action. And obviously by doing so, agent changing the environment. And it gets us a new state with the additional information, which is called reward. Reward is like a feedback to the agent, how good was the previous action. And it can be positive, neutral, or negative. And usually reward is being used during a training. So there is an observer who can kind of judge how good was an action. And that's what we called offline trainings. But during the play, agent doesn't have this information and doesn't get the reward. It just has a state and can make an action. But there are some algorithms in reinforcement learning now where it can be online training. So it will be improving every time. So it gets the information about the state and it can calculate the reward. So this is just an overview to make the next slide clear. So what we can see on this slide is actually a full submission to this Kaggle competition, meaning that you can, like by the end, when I describe this slide, by the end of the slide, if you have your account open on Kaggle, you can just write it down and make a submission, and you will get a result. So what do we have here? First of all, we need to install Kaggle environment and import some of the libraries. Then the libraries are very limited, and that's one of the reasons why we didn't submit the reinforcement learning agent, because what we have here is just basically a NumPy, SciPy, and PyTorch on CPU only. But that's not the only problem. I will actually, we can see that in the end, we just tried the agent file, which is submission.py, and it has to be just one file, meaning that we cannot provide a model, even if you try some kind of deep reinforcement learning agent, and you have a model with the weights. There is no easy way to provide it here. people solved that problem by using base64. Basically, they just put the binaries in there, and but there is still a limit of I believe 1 megabyte. So the model that you can build should be like really, really small. And yeah, the engine itself here on that slide is just 3 lines of code. As you can see, there is a function called myAgent. It takes 2 parameters and it returns 1 number. In this case, you can see that this is just a random choice. So it takes a random column. And if it's a valid move meaning that the column is not full. So if there is a space available in a specific column, it just choose it randomly, and that's it. It actually works. If you can do submission right now, you can end up, in the end of that leaderboard, and you wouldn't be a last because all the last dozen agents are just the ones that time out or have some kind of error. So that's a good submission that you can do right now, but you can improve really pretty easily on that as well.
Alexei?
Yeah.
What's going on here when it does Kaggle environments.make Connectx? Like, what does that load up?
I'm sorry, where is it? Which line is that?
It's just below the imports.
Sorry, I'm having...
So env equals make Connectx.
It's just create the environment. So it does create this environment that has the observation and configuration. So we will go over that on the next slide.
Okay.
So let's talk about what it actually has as a input. Those 2 input parameters, observation and configuration, coming from that environment that Dan was it Dan? I'm sorry, I couldn't see.
Yeah, that was me.
Yeah. So the Dan was asking about, and what is an action? In terms of input, we do have 2 parameters. One is configuration that has several options there. So we do have 2 limits, which I already talked about: the timeout, the execution time in seconds. Right now it's set to 5. But it used to be 2. When the competition started back in January, it was 2 seconds. But the reason for that, I think that they changed the timeout is just when they added the PyTorch. PyTorch was added just 2 months ago. So in the beginning, this competition had only NumPy available. And that's why rule-based solutions were the only option in the beginning. The number of steps that you can run the environment is also set to 1,000, which is not too much. And it actually prevents from some of the algorithms, especially in the reinforcement learning, that you could use. And that's the couple of other parameters answering Alexei's question about why is it Connect4? Because in arrow is set to 4 and you cannot change it. And the columns and rows, obviously, like the board can be bigger, but in this case, it's standard 7x6. In terms of observation, what we have here, we have a mark, which is basically assign you a turn, 1 or 2. You can think about it as a colors as well, but white and black, as Dan was mentioning. Yeah, if you have number 1, so you have a better chance of winning. And board, the board itself is just this is the environment that is interesting to reinforcement learning agent, and it's just a list of numbers 0, 1, 2, and I reformatted that in a grid so you can compare how it looks like in terms of like actual picture or actual board. And output, so you get this information in and you have to decide which action to take, which is just a number, a column to drop. Okay, let's talk about a couple of rule-based solutions. So as we discussed on the solution slide, one of the simplest methods that we can use is one-step look-ahead approach. And what we do here, we just, from the current state, we just evaluate every single move that we can make, and we assign a score to each move. To assign the score, we need to choose a heuristic, which is basically usually a number. And the heuristic that we can choose, it depends on the type of the game we are playing. In this example, on that picture above, we can see that a winning move gets 1 million score, and the losing move, or like a move that is probably will be losing, gets us minus 100 points, and the move that brings us closer to the win gets 1 point. The one of the heuristic they missed on that slide is the move where it's basically neutral, and if the move is neutral, you get a 0. But you can think about that as a hyperparameter, because you define what the score will be. And if you think about that, it's actually a hyperparameter where you can use a deep neural network. And that's what reinforcement learning agent will do. It's basically, this is like the main thing here, to define a good heuristic, which we can do manually, like in this case, or it can be some kind of algorithm. It can be neural network, for example. And in one-step look ahead, you can see that the next we have to select the move that gets the highest score. And for example, as you can see in here, the leftmost option that we have, it's actually the best move because it will lead us to a winning move. Because you can see that we can, whatever the yellow player will do, we can actually win in the next move.
Wait, can I ask you a question about that?
Sure. Yeah.
Does it add up those colored order things, the points from them, only that have to do with the marker that you just put in, or is it over the whole board?
No, we haven't put the marker yet. We are just thinking about which column we should choose.
Yeah. So okay, say you choose like the second column, and in this example, it doesn't really show what I mean. But say you choose the second column, then in your example, you get 1 point because there's one of those sequences. But say over on the right side, there was another one of those sequences just sitting there from before. Would you get that point as well? Like it's not, it doesn't work with this example, but I'm making like a new hypothetical example.
Well, if there was, it's actually says on that slide, if the multiple moves get the high score, I guess that's your question.
So you would still get that extra point from any sequence which does not involve the hypothetical new marker that you put in, even if that sequence like already existed? I don't think I'm wording this question very well.
Yeah, I'm sorry. Maybe Robin, do you understand? Maybe somebody else can answer that. I just don't understand the question. I'm sorry about that.
Like in all these examples, the sequences that are circled involve the hypothetical new placed marker, right? But if there was another sequence that fit one of those patterns that existed regardless of whether or not you put that marker in its new hypothetical location, would you also get points from that sequence?
If you had an existing 3 in a row and you dropped another marker, you'd have the goal and the game would be over.
True. But there could be multiple. Okay, sorry.
There might be a 3 in a row that there's no place to drop to complete, right? Maybe that's the case.
The one thing that's not taken into account is when you stop your opponent from getting 4 in a row, if that makes sense.
Yeah.
Yes, and this is like a very simple algorithm, so it doesn't take in consideration many things, like what your opponent will do, right? It doesn't think about that.
Okay.
This is like, as I said, this is the one that my toddler would do. Like, he doesn't think 2 steps ahead. The next algorithm that we're gonna describe, that's exactly the one that actually goes like deep into the decision tree or game tree in this case, and thinks about all possible moves on the net for your opponent and yourself next, and you can define as many moves as you want for the depth of this tree, but obviously it grows exponentially. So there are 4 trillion like possible moves when you start, like in this example, when you start that game, the whole board is open as you have 4 trillion possible scores. This is like a very strong algorithm, and I was surprised. I never thought about that, but it's actually the algorithm that was used by Deep Blue in 1996 to win a chess, the champion of the world, Kasparov at the time. And that's what they used, optimized, but actually it was just, I would say it's like a brute force, right? So you just go over all possible moves. We will discuss some of the techniques they do for optimization, but that's what works in chess. And for Connect4, they achieved that when they actually brute force all possible scores in 1995, so 1 year before chess. It didn't take too long for a chess, but for Go, which we will discuss later and Robin will present, it's different. I actually probably need to speed up because Robin said that he needs 30 minutes and it's already too much. So exactly what is happening in MiniMax is just in this example, actually the heuristic, just based on the numbers, I can say that maybe this is chess. Why? So we do have a different scores for different outcomes. Let's say we have plus 40 if you get to capture a queen. And let's say you get plus 10 if you get to capture a knight. And plus 1 if you get to capture a pawn, something like that. So you define a heuristic. What do you think? Like, what is better, knight or rook? Like, who knows, right? Or knight or bishop. Like, you have to define as somebody who creates this algorithm. But how it works is that you have to choose your move, and you have like many different options. In this case, we are looking only at 2. And let's say on left, you need to move a pawn, and you can move a pawn, and you're thinking about what your opponent will do, and depend on the outcome. You can see that there are 2 outcomes. You either get with that pawn, you can either get the queen, or your opponent can just take this pawn out. As you can see on the left, plus 40, that's the best outcome for you as if you do that move. But on the 0, probably that would be like if that queen just moves away and does nothing. But the worst outcome for you is that it actually takes your pawn out. So, and on the right, you have a different kind of like a play and a different type of move. Let's say you have an option to move your bishop somewhere on the board. And both outcomes in this case are actually positive. You either take the opponent's bishop, or you take opponent's, let's say, rook, if it's assigned a score of 30. So need to calculate for every move, for every possible scenario that you have, all of these leaf nodes, and then you move to that second part of this picture on the bottom, where you have to take a maximum outcome for yourself. So you kind of like trying to maximize your score, but you have to understand that that level above is something that your opponent will do, and it's trying to minimize your score. And that's why you can see that, no, you shouldn't like actually go on the left. You shouldn't move your pawn. You should go with your bishop and go take this right option. Once again, obviously, if you look at that pseudocode and it just describes that in with a different heuristic, it actually closer to the heuristic I would choose for tic-tac-toe, because it has a value of minus infinity and plus infinity for you and your opponent for positive and negative. And what you can see here is that it's recursive algorithm, and as any recursive algorithm, like it goes exponentially in terms of like performance. It becomes worse and worse. And there are a couple of things that you can do to improve that, and that's exactly what Deep Blue used. First of all, you can use NegaMax, which is just a simple idea that anything you're trying to maximize, your opponent trying to minimize, and that's basically, that's why you can, when you do the calculation, you can define that function as a maximum score for yourself and minimum score for your opponent. So you don't need to do calculation twice, do the calculations only once. And then for alpha beta pruning, it's very simple idea that, let's say in the previous example, actually, that would be good. If you go from right to left and you see that you have a really nice move on the right branch, so you calculated plus 10 as a value, a score for that branch, and you go on the left and you see minus 20, minus 1, you say right away, like, I don't need to calculate anything else. I can just, like, this leftmost branch, I'm not going to do that. Doesn't worth it because I'll be losing anyway. So the pruning works pretty well. And then just based on that example, you can see that the move ordering becomes very important. So there are some options, there are some methods to improve that ordering to make sure that you get that answer really fast. And also you should be pruning all the branches where you can see that it will be a losing move right away, so you'll be losing the game. And there is also transposition table. The transposition table is basically a caching. Because if you think about that, if you start using MiniMax many times and you kind of look at the same branch once over again, like over and over again, let's say you have a bishop standing at one point, right? So you can see that many moves by this bishop will have the same outcome, and you don't have to recalculate it. So you basically cache the scores for your next move and maybe next move, but that's the idea of transposition table. And yeah, as I said, this is basically a winning solution. Unfortunately, just because people do have lots of ways to optimize that algorithm, and it's like a brute force, and it's the best solution you can use for this specific example, but not for every problem. And hopefully next competitions will have something that cannot be brute force. And that's where the reinforcement learning comes in. And yeah, I hope, let's stop for a second. Do we have any questions about the previous slides before we move to Robin's presentation?
Yeah, I had a question.
Okay.
Just quickly, if we're doing reinforcement learning, does our model start from scratch each new game and has to relearn as it goes, or is it taking knowledge from a previous game and bringing it to the next one?
Well, I think that Robin will answer that. I can, but that's something that Robin has in his presentation anyway. So
Yeah, it'll carry across the games, and we'll get more into that.
Thank you.
Okay. Yeah. So if there are no more questions, I think Robin, you can take it away.
Awesome. Okay. Thank you.
Can you stop I cannot stop my sharing. So
oh, right.
Screen sharing. So please.
Okay. I'm gonna share my screen. Can you guys see? Okay.
Yes.
Yes. Now we can.
Lots and lots of icons. Oh no, now it's a presentation.
Okay. My presentation's got pretty dense, so we'll see how we can get through in time. But basically, I've tried to pack a few different ideas in here. Now, the reason I'm packed a few different things in here is I tried to submit an agent, but at the last minute, I realized it has to all be in one file. And so I was working on an AlphaZero solution, and I just couldn't submit it. So I thought, well, I'll spend some time talking about it instead. So high-level reinforcement learning, it is really, there's a loop, some kind of environment and some kind of agent. The agent's choosing actions, submits to the environment. The environment is emitting states and rewards back to the agent. But this loop is unrolled over time, and unrolling the loop creates the structure, or you can say the agent is navigating the structure of what's called a Markov decision process, which is really a variant of a Markov chain. And the word Markov means that at every point, the state is everything you need to know to make your next choice. So the state could include some information about the history if that's needed, but you don't have to worry about the past. You just knowing the present state. So a Markov chain just has states that are connected. The Markov decision process adds some special features to the Markov chain. That is these actions. You can take a choice, a decision at states that lead to other states, and depending on the actions, the environment can emit rewards. So these action transitions and these rewards are added to Markov chains to make MDPs. Now,
so sorry, just jump in just to emphasize in the case of Connect4, the significance for Markov is when I look at the board, like it doesn't matter how we got here.
Yeah.
Like what order of past events led to the state is irrelevant. It's just where the pieces are. Yeah.
Exactly. Yes. Thanks. And okay, so this is RL in general, but when you have more than one agent involved, then we call that multi-agent RL. And multi-agent RL is a huge field. There's many different types of it, but here we're talking about a competitive situation where the opponent is aware of its opponent. We'll talk about that in a little more depth. So with competitive multi-agent RL, we often call that self-play. What is self-play? Self-play has been applied to board games, games like Dota and StarCraft. And if you think about these domains that self-play is used for, they have some specific things in common. They're very easy to simulate, and there's no real-world domains in here. People choose domains that have strong opponents, either in software or human, and they choose domains in which exploration is somehow tractable. So it's not, self-play RL is not always applicable, but it's kind of can be cool when it's applicable. And some people say, oh, is it, any agent playing with an environment it's self-play, but this is actually, it means specifically when it's an agent playing against either another agent or a replica of itself or itself in the mirror. And self-play has some specific, self-play is a very specific type of RL, and it has some interesting properties. So let's talk about how it applies to Go. Why am I talking about Go? Because I wanted to do an AlphaZero submission to this competition, and that's what I worked on. And using somebody else's code, by the way, I didn't write AlphaZero from scratch, but I was, working with this code base and training and modifying it. And AlphaZero, of course, was famously applied to Go. So the game of Go, it's the surrounding game. It's an ancient game associated with agriculture, but for our purposes, the properties of Go that are interesting are it's perfect information. So that means you see everything the other person sees, and both players can see the history. They know what happened. A zero sum, that means if you win, the other person has to lose. The total score between the two players is fixed. Deterministic, so there's no chance. Nothing happens by chance. And it has a very large action in the state space, and that's important here. So if you look at all the, I made this chart from the data from Wikipedia, and I plotted it, showing the state space complexity and branching factor for a whole different bunch of types of games. Now Connect4, so they called it Connectx in Kaggle because the simulator, you can actually change the X in the simulator. But for the competition, they fixed X for 4. But the simulator that they give you can be used for any size board. But for the standard size, you can see it's down here, tic-tac-toe on the bottom left. And chess, you can see, is a lot less complex than Go. Number of particles in the universe is over here. So Go, number of states is way beyond that. It's pretty crazy. So this has implications in what you can do. Like, so AlphaZero, they figured out a way to have AlphaZero only look forward tens of thousands of moves. A human grandmaster, they say, thinks through tens of moves. Chess engines, tens of millions, and I added for context, Deep Blue was looking at 200 million moves per second. So you can imagine this is the brute force solution on the far right. So clearly AlphaZero is not doing brute force, at least not at the time when it's playing. So on the highest possible level, what AlphaZero is this loop between a tree search and deep learning. So Alexei walked us through MiniMax tree search and those type of algorithms. So that's this part is that's related to this part, but then it interleaves it with deep learning. And so the result is, if you look at the MiniMax tree where it's just like doing a uniform exploration, the difference here is it's a smarter search, and it searches some areas, more promising areas, more deeply. And that's the key. That's the reason why they can get away with having so few moves, is because they're very carefully choosing. The deep learning is helping to carefully move to the most optimal position. They can skip a lot of moves that aren't promising. So how does it actually proceed? So it does Monte Carlo tree search, and we'll talk about that in more depth, to choose the moves. And that involves using a policy network and a kind of complicated process that we'll discuss. And as it goes through, it plays a simulated game in its mind. This is the training process. And it comes out with a Z, that's the result. So a +1 or -1 if it wins or loses. And then it feeds that result back into train the value function. And also and then it uses the counts. It uses kind of like the trace of how often it explored certain paths, because it always explores. It's designed to explore the more promising path more often. So if it takes one path more often, then that's a higher quality path. And so when it's done a simulation, it can look at the paths that it did more often, and it knows that those are the most promising paths, and so it trains the what's called the policy function to match that, and that's what I mean by this loop. So it's using the tree search to provide targets for the neural network, and then it loops around like that. So in a little more depth, on the left you can see the network. This is a ResNet, and it's a really quite a large ResNet. And it's one network that has two heads. So what goes in is the basically tensors representing the board state, where all the pieces are, and what comes out is the value and the policy, and we'll talk about that in more depth. The loss, I mean, you can really understand what's happening here if you look at this loss. So there's two main components to the loss. It's learning the value function with the mean squared error, and it's learning the policy probabilities with the cross entropy, and then there's a regularization term. So let's look at that a little more. So this is the Z is the actual winner. It's a +1 or -1, and then the V is what the value, the value head on the network outputted. and that's a scalar. And then the policy is a vector over all the actions. And then the P is taken from the Monte Carlo. It's looking at what actions were actually taken in the rollout. So it's trying to make, what it's trying to do is it's trying to get the deep network to match what happened in the tree search, so that it doesn't have to do the tree search. It can just use the network to predict what the tree search would have done, because the tree search is very expensive. So they're making it cheaper by learning how to do, by learning the result. So the tree search is quite in depth, and the way it proceeds is for each step, for each iteration, that means rolling through a game in the training process, it keeps track of all these different statistics on every node. And so the Q and the N's are these counters that are being tracked on every node of the tree, and updated as it goes. And then the P's are the policies from the network. And the way the tree search is controlled to make it more intelligent is every node has this estimate of called the upper confidence bound of the Q value. That means if we were to be optimistic, how good could this move possibly be? Now, before it does a rollout, it doesn't really know. It doesn't have. It has zeros in all these stats, so it doesn't have that much information. And then what it'll do is it'll simulate a game through, and it'll update those stats as it goes, and then it'll keep for each move, and it'll keep doing that. And as it goes, the stats get more and more filled out, and so more and more informative, and that changes the upper confidence bound for how promising it thinks certain moves are. And there's a term over here. These terms have to do with the counts of how many times it's visited a certain state and with a certain action. And so what this does is it says, well, states that I've visited more often, I can be more sure about. Certain states that I've visited less often, I can be more optimistic. Maybe that's promising, right? But after it has more evidence, then this goes down. So it's kind of on every single run pass through, these stats are updating, and these confidence bounds are these upper confidence bounds are changing, and that's part of the exploration here.
Hi, Robin.
Hey.
I have a question. Okay. So, what's this sigma_b? What's it? What's the meaning? This parameter. What does that mean?
Yeah, that's
sigma_b. Is it?
That's summing over all the actions. That's saying how many times.
The sigma. Oh. Okay, got it.
Yeah. So I'm not going to go through this whole thing, but just I want to point out a couple things on the Monte Carlo tree search algorithm. So when it does a search, there's only one step here that involves the neural network. That's the prediction of the policy values. The policy and the value function. And it does that when it's doing the training process. It only calls the neural network when it gets to a node that it hasn't seen before in this round. And if it hasn't seen it before, then it calls the neural network. It stores these values, and it returns that to the Monte Carlo tree search, the part that called that. But if it has seen it before, then it updates the statistics. And here's the part where it does the upper confidence bound calculation. And then you can see it figures out what is the most promising move. It picks the best action according to the upper confidence bound. And then you can see it continues the search from there. So it picks the most promising move and then continues the search. And this is recursive. So that's kind of the inner core of AlphaZero. But then outside of that, if you step up a level, what it's really doing is called policy iteration, and the Monte Carlo tree search that we looked at before is just this one line here. But these two levels above, on the highest level, what it's really doing is it's collecting training examples by executing episodes down here, and it's collecting those examples, and then it's training the neural network on those examples. And then once it's trained, once it's gone through the training, it then compares itself to the previous iteration of itself. And if it's better by a certain amount, then it replaces this version of the neural network. So it's kind of making a trail of sequence of versions of itself, and always comparing to the last version. And if it's not much better than the last version, then it just kind of throws. It doesn't. It always keeps track of the best version, basically. And so, yeah, I just wanted to point out that here that it trains itself, and then it evaluates. So it's constantly evaluating, how am I doing after this training?
Hey Robin, sorry, just a quick question here. Is there a limit to the amount of recursion, or like, is there a depth limit to the tree, and like, where would that be specified?
Yeah, there's well, when it's training, it plays the games all the way through, right? Okay. But when it's running in test mode, then there's a parameter for how much. Actually, it's true in training too. There's a parameter for how much of a tree search to do, but it's not a depth. It's not defined as a depth. It's defined as how many times to call the MCTS. And the way the MCTS works is it continues, it maintains one tree in memory, and it just keeps running. But then when it gets down to a node that it hasn't seen before in this run, then it stops, calls a neural network, fills in those probabilities, and then goes to the next iteration. So it's not, I would say, and I might be, I'm not 100% sure this is correct. So actually I should step back from that. But that's my impression.
No, I actually agree. I looked at that for a few days now, and that's exactly how it works, I think. And also so it goes like all the way through. So it doesn't go like to the specific depth. It actually plays till a terminal state. But I was surprised about the fact that it's playing a random games. So it's not trying to pick the best game. It just plays, I think in that algorithm, they're using 1600 random games, but all the way through to the terminal state. So I think that you're right.
Yeah, but but controlled randomness. There is some randomness, but it's directed as well. Yeah.
Well, yeah, well, you're already in the specific branch of the tree, right? So it is controlled, but then you roll out that it's kind of random.
Yeah, and yeah, absolutely. I'm not sure this answers the question fully, and there's a lot of guys. There's a lot of details I don't really get yet. But pardon?
It helps me at least what you said.
Yeah. Okay.
Sorry, Robin. Another quick question. Been curious about how AlphaZero does this. It's not directly related to this particular problem, but so related to what Alexei also said. So do you only get a reward once you finish a game and you get a win or loss, or is there a concept of how well you're doing before you win or lose?
Yeah. Well, the value function head is always telling you. This
at any point in time, you have that, right? Okay.
Yeah, at every point in time, it's giving you a probability of this side winning.
Gotcha.
And so you have that for every single board position.
Right.
Okay, and then so the input features are like these planes. These like kind of like an image would have multiple planes for the different RGB, but there's a different plane for every type of piece. And then this is for Go. And then there's another plane just for the color. But notice the player 1 stones and player 2 stones are on separate planes. The input representation is more complicated for these other game types. I'm not going to go through them. But for Connect4, it's also, you can actually, it's very simple, so you can use a similar input representation. Very clean input. For chess, the output is a pain in the ass. Okay, for other games, the output is very simple. The policy, once again, the value function is a scalar. So it's saying, what is the, who is probably going to win this game from this position? And that's +1 if it's player 1 and -1 if it's player 2. So the value function is always providing that. The policy head is basically like a bar chart over all your actions, and it's giving probabilities on every action. Probability that that's the best action to take, basically, to help you win. For Go, because in Go the move is very simple. You just pick a position, you place your piece there. In chess, a move is complicated. You have to pick a piece, and then you have to decide where it's going to go. It's like a 2-step move. So the output for chess is a nightmare, and I'm not going to go through it, but it's for AlphaZero chess, it's more complicated. Here's some stats on training. So if we focus on Go, yeah, it was done in, this is saying 34 hours. And here it's saying 800 simulations for every move and 200 milliseconds. So what does that mean? That means it's playing, for every time it has a move, it thinks through 800 games, basically. And sometimes I've seen this as 1600, so I don't know what the, the thing was with AlphaGo and AlphaZero, there's so many variants. So there's different stats that float around. So in reinforcement learning, the general idea is learning from experience. You can't really do that if all your experience is the same. So what is usually done in reinforcement learning is they try to add some variation or noise, and it's called exploration. So trying different moves to see what works, right? And that's only possible with randomness. So there's actually 2 types of randomness that's used in, there's 2 types of forces that are at play for exploration. One is this end term here, because the multicolor tree search is keeping track of how many times it's seen a certain node. So it can prioritize those nodes it hasn't seen very often. So that's kind of a form of exploration. It kind of puffs out the tree to look, to not get too fixated on things to not ignore states that it hasn't, things that it hasn't tried yet. But there's also another type of exploration that's added on top, is this Dirichlet noise that's kind of added to the probabilities. So what the standard policy output is like that. What it does is it takes, it mixes that with some Dirichlet noise. Dirichlet noise this is symmetric Dirichlet distribution, which means a Dirichlet distribution where all of the values have the same alpha, and all that means is depending on the alpha, you can get like a very uniform type of noise or a very very spiky type of noise, which prefers a few positions. I should have had a chart for that, but basically, and this is only used from the root node. So the point of this is to add a little more variation to the experience while it's training, and they would not use this during gameplay, during the final gameplay. This is to allow it to branch out a little further and not get over fixated on certain paths. So because of that chart I showed before about the branching factors and the state space, I guess they figured out that these alpha values are the best for the different game types. So when you apply a new game type, I kind of broke the AlphaZero implementation I was working with because I was adding this Dirichlet noise, because they actually didn't have Dirichlet noise in their implementation. I thought, hey, we should add that like the paper. And then so I was trying to pick an alpha, and I mean, it was kind of working, but I probably broke something, but it was fun. Okay, so so that was AlphaZero. I'm gonna jump very briefly into DQN, so just to compare, because another thing I tried was DQN on this type of game. So let's just very briefly look at DQN. DQN are deep Q networks, and that was basically the very first deep reinforcement learning algorithm that came out of DeepMind back in 2013. And that DQN played Atari, and DQN was a CNN, convolutional neural network, that would take in basically the Atari screen and output joystick actions. So it would output a vector of basically a value function for each, called a Q function, meaning it's really just a value function, but it's saying, well, if I make this move, then how good is the state I'm going to end up in? Right. So this is it's a little different setup than AlphaZero. And if you look at the loss function there, it's different than very different than the loss from AlphaZero. The loss function here is actually includes the outputs of the network itself right in the loss function, which is kind of weird. And I'll talk a little bit more about that. I think the weird, to me, when I first saw AlphaZero, I was like, why do we need such a strange algorithm? Because it's so different than DQN, right? So I want to contrast those two things. So let's look at AlphaZero versus DQN. So first of all, in the domain, the number of moves in Go is just way larger, right? We have just 16 actions in Atari, and in Atari they're counting, you know, a button press and a move as a separate combo. And so in Go, you have many seconds or minutes for every move, right? In Atari, you want to move quickly, maybe milliseconds you have to choose your next move. You have to be very quick. The network's a little different. In DQN, the layers are just the previous 4 frames of the screen, so you can tell, the network can tell a sense of motion. But the target in AlphaZero is these Monte Carlo tree search results, right? That V and the pi. But the target in DQN is really the current reward plus the network outputs. So we saw here the target here is the current reward and plus this term with the network outputs. And the loss is just the mean squared error on the Q value for DQN, but we saw the loss for AlphaZero included terms for the value function and policy separately. And then the exploration strategy is totally different. In DQN, just once in a while it takes a random move. That's epsilon greedy. In AlphaZero, you got a sense, hopefully you got a sense of how in-depth their exploration strategy was. It was really intense, where this is the absolute simplest exploration strategy. And then in terms of selecting next move, AlphaZero does this very fancy and expensive thing of running all these simulations and adding up all this bookkeeping. And DQN just simply does one run through the DQN network, looks at the outputs, and picks the largest one. So taking an action is very quick and cheap here and very expensive here. And so why are these two things done so differently, right? Both of these are from DeepMind. And the reason is when you look at this agent environment loop, the agent really needs to be designed with the properties of the environment in mind. And these environments, which are really MDPs, all different MDPs have such different structures. You can see up here, like how many possible actions, that branching factor, how many states there are, how much time there is to think about it. All these different properties result in many different design choices and trade-offs in the design space of agent. And so they took advantage of those, and they came up with 2 very different solutions. These are both deep reinforcement learning, but they're extremely different.
Robin, can I ask? So on the loss row, MSEQ and MSE value, those are very similar in concept, right? I mean, they're essentially predicting the value of a state. Is that correct?
Yes. So a Q is a value function, but it's actually a state action. The value is a state value, and the Q is a value of the state you would get to if you took that action.
Oh.
So they're related, but they're not identical.
I see.
So what this is saying is if you do that move, then the value will be that. The value of the state you'll get to that next. So what that means is it lets you, this formulation lets you summarize a whole bunch of value functions, results together and choose. But that doesn't happen in AlphaGo, in AlphaZero. In AlphaZero, you just get the one, where is it? You just get the one value, you just get the one V scalar out. And that's with respect to one board position.
So in the queue kind of gives me, like in one branching of the tree, it gives me the values of all of the next possible steps.
Yeah, it values each action according to the value of the state you'd end up with if you did that.
Okay.
Yeah, so this slide is really what I wanted to convey. And so let's just look at, so DQN, very cheap to compute. Up here is petaflop seconds per day. This is kind of an old slide, but it's still relevant. You can see these are self-play, and AlphaZero is way up here. This took a lot of compute. You cannot really compare how much more compute it was to DQN. It's night and day. So the AlphaZero algorithm, as weird as it is, it applies to zero-sum games of perfect information, but you wouldn't want to use it for all such games, right? It requires a perfect model. Perfect model means that the agent can think through, well, if this happens and then that happens and then this happens, and it can think through like 50 or 100 or 500 steps ahead, and there's no degradation in the quality of the estimate of what's going to happen then. It's perfect. That's often not the case. It needs a performant model. That means that when it's simulating, thinking through, if I do that, then what's going to happen, it's having to call some function to estimate what the next state is. And if that function is very expensive, for example, if you're trying to simulate the whole traffic system of New York City, it's not going to have these properties. It's going to be very slow to do every step, and it's not going to be perfect. So you're not going to be able to plan 100 steps ahead, and it's not going to be performant. So what I'm saying is this algorithm only applies in very certain conditions. You only really need this type of in-depth algorithm. The specific form of algorithm is only really going to help you at all if your value function is very bumpy and jagged and hard to predict. So why am I saying that? Well, in Atari, think about it in Atari. How confusing is it to realize that you're about to die? It's usually pretty obvious, right? That means the value function is smooth. It's kind of obvious that you're either doing really well and you're about to win, or you're doing really badly and you're about to die. In Go, it's not like that. One piece can suddenly drop in the board and completely change the situation in terms of win-lose. And you're like, holy shit, that means that has all these other implications. Basically the win-lose ratio can change dramatically with a small change in the board state. And so I believe that is why AlphaZero, they needed something like AlphaZero, and why they couldn't use something like DQN. And I think I've heard David Silver say this actually, that for Go, a value function alone just cannot capture enough detail to cover the space. So that's why they're doing this tree search, so they can kind of look around the corners basically in the strategy space. So I wanted to just point out that on the right here, you can see different versions of AlphaGo 0. You can make AlphaGo or AlphaZero or any of those systems, you can make it play like DQN, like in an instinctive way. That means just take the policy outputs, like just stick in the board state to the network and just look at the policy outputs and just make that move. That's not the default way of playing it. The default way of playing it is to use this as part of this extensive simulation for every single move, to do many, many simulations interleaving the tree search and the network, and the tree search and the network. But you can just strip all that away and say, look, I'll just take the network and I'll just stick in my board state and take out the probabilities and make that move. And if you did that, you get this gray bar. So it's still pretty strong, but it's nowhere near as strong as if you do the full Monte Carlo rollouts for every move, doing all these simulations. Yeah, so that's AlphaZero. I put a bunch of references in here. If we have a few minutes.
Yeah, I think we have 1 minute, so probably I will go over the winning solution.
Yeah, okay. I'll
and it will take me exactly 1 minute. So how do I share the screen? Creating a winning solution. Here we go. I think it will take me 1 minute. So, so there was a discussion, and I have a link here at the bottom about the winning solution in this specific competition. It actually dropped after 2 months. It was on the top for 2 months. And what the author said that they used like a perfect agent, kind of perfect agent, because they didn't have the full open book. They had to fill in the book in 1 megabyte, which is impossible. The full book is like 40 megabyte or 64 megabyte. And also they have a MiniMax solution, but they're limited to, like everybody else, 5 seconds. So how did they solve that? Oops. First of all, that the winning solution was written in C, and how people, they loaded models as base64 binaries inside the Python file. They did the same for these C files. And to store each position, they used just 49 bits and each move 3 bits, possible move. And they didn't store any terminal positions because what's the point? It's already lose or win. So, and they also have a full open book for first 12 moves. And they had kind of like not winning moves, best moves for up to 26 moves. So kind of like they had open book just for a beginning of the game. And why is that? Because they can use MiniMax later in the game, and it's easier to go deeper in the game with the MiniMax when you have already many positions closed. It's much easier to calculate, and you have a better chance of winning if you had perfect moves in your first part of the game. So, and that's a winning agent. And I guess like top 20 people actually using that. And all reinforcement learning solutions, they were kind of like after that. So like after top 20, but still they're doing pretty good. I hope they will have a better option to load the model, and maybe we will be able to upload that agent in future. But otherwise, I think we are done. And we can have a discussion if you want about the fact that why agent cannot win that. The reinforcement agent and even AlphaZero cannot win that game. But I guess that's
sorry, Alexi. So I'm curious.
You have to be really good at training it perfectly, and it's going to be really hard to compete with that perfect.
Yeah, if you know the like perfect moves,
it could never outdo it. It could tie it, right? I guess.
Yeah.
So I'm curious, Robin, since you went through all the trouble of getting the AlphaZero thing working, did I understand correctly that the issue was that it couldn't be fit into one file? But if you remove that restriction, can you match the performance of the best agent?
So what I did was take Surag, this guy Surag, and he has a GitHub, and he has a AlphaGo implementation, which actually I have a few slides on it. But basically, I took it, and he already had it working on different game types. He even had the Connect4 game, but it was on TensorFlow. So I converted that to PyTorch, and then I added this Dirichlet noise, and then I trained it a bunch of times with a bunch of different hyperparameters, and the performance was pretty bad. Like,
okay.
My experience training it is that AlphaZero has so many hyperparameters. Okay, even like it has all the normal reinforcement learning hyperparameters and a bunch of other ones that control the MCTS. So I really didn't know what I was doing with the MCTS. So I was trying different parameters, and I was playing. Like, I got some. It would make some good moves, but it was nowhere near perfect. Like, generally, I could beat it at the level that when I was training it for like a day.
So the other thing I would be wondering is, it looks like with AlphaZero, you're trying to use a bazooka to kill an ant, Like, what if just using, did anyone use like linear function approximation with just normal RL to try to solve the game? I think that should be sufficient for this simple of a game.
Yeah, I don't think that would work that well, honestly, because of so many different variations. I don't think that would play very well with a look-ahead tree, because what happens is, as you get more deeper into the tree, the agent would have seen those positions fewer and fewer times. And as you get very deep into the tree, it's very likely that the agent has not spent much time training on those, and that other positions have kind of skewed the queue function for those areas. So I think it would be actually really challenging to do that.
Okay, cool.
Yeah. I mean, yeah, I think the value function on these games is very bumpy. Go much more so. And also the board representation I think the border representation is important. So in this, in the versions that I used, it was just one board that had ones or minus ones in the different positions, right? But in the official AlphaGo and AlphaZero, they didn't do that. They had separate planes for every player. They separated it. That means your convolutional neural network can easily scan across and see that there's the difference between, like, it doesn't need to get confused by the other player for certain channels. I don't know if does that make any sense?
Yep, makes sense. Yeah, I totally agree that representation is almost everything, like how you represent. That's why I kind of don't like DQN, because they learn from pixels, right? Which is, of course, the first thing you try, but how you would actually organize your states. Like if you could, in theory, organize all the states that have the same value into one bucket, you know how much easier that would make your search. Of course, we don't know how to do that, but it's just, if you could, you can imagine a coordinate system where all the states with the same value are in different buckets, and you just pick the right one, and that would make it so much easier, right?
Yeah, well, that's what the queue function, the training the queue function does. Like they did they showed a Teasney plot of all the states, and it clustered together the ones that were similar in that way.
Okay.
So this is the border representation in general, which is the open source version that I was playing with, just does a straight minus ones and plus ones, but it's all in one plane. And so you can see it playing here. Here I'm playing it. This is AlphaZero. I'm one here. I'm trying to win along here, and AlphaZero made that move, so it blocked me. But this is with very few pieces, right? So what I found is it got worse and worse as more pieces were added, and I didn't know. I was like not calibrated in how long I had to train it for, what the hyperparameters were, and there was no official model in the repo for Connect4. So and here you can see it's training. It's dealing with the policy loss and the value loss. Is there something else I wanted to show there? Yeah, I did the same. So I did 2 years ago. I tried to do this Connect4 with DQN, and I did a slightly different setup. I embedded the opponent agent in the environment. I treated the opponent as part of the environment. I used a separate agent, a separate DQN agent for that, and I ran it that way. And I used the same board representation as with the AlphaZero agent. And again, I mean, I never got to great performance with the system, but it was very educational to do that. But this is different than how AlphaZero does it. The way AlphaZero does it is there's only one agent, and when it takes a move, then it multiplies the board by -1, so it flips all the colors of the pieces, and then it takes another move, and it just keeps doing that. So it doesn't, like early versions of AlphaGo actually did have two networks like this. This would be like the older network, like the previous iteration or previous iterations, even in training. But the more recent one, AlphaZero, is like playing in the mirror, basically.
So what you're calling AlphaZero, is that the same as MuZero?
No, MuZero is a very different thing, and MuZero is AlphaZero type system that doesn't know the rules of the game. It doesn't have a model built in, and it learns the model as well as the rest of it.
Okay.
Yeah, I actually talked to David Silver about MuZero at his poster at NeurIPS, and I was like, "So, David, how does MuZero deal with stochastic models?" And he said, "Actually, it doesn't. It assumes a deterministic model." And then I was like, "This is not going to help me at all with my use case."
Not going to help anyone.
Honestly, it won't help much. So I was kind of like, okay, whatever, because like what I feel like this stuff is very cool, but I feel like it only applies, I think, as Payam was hinting at, it only applies in very specific situations, and I think we've kind of overinvested in those scenarios in general, as you can see on the compute charts. For some reason, people really want to burn a lot of compute on these deterministic environments, which are not very realistic. So I'm not focused on that stuff.
I'm going to jump in as the host. Was put a cap on the presentation. I don't want to put a cap on the discussion, but this will wrap the video out nicely, perhaps. That was really great. I'm really glad I made time for this. So thank you to our presenters, Robin and Alexi. We try to do like an applause thing. I don't know, Bruce, do you want to hit like the all unmute button, or do we want to even want to do that? I don't know. I think it's fun to have stupid traditions.
I think it's fun to have stupid traditions. I did the unmute all. People kind of have to accept the unmute, I think.
Yeah, all right, so we're going to have a little applause. It's not going to be quite like singing together, so it might work. In like 3, 2, 1, yay! Hey, that works pretty well. All right.